And namaste everyone. Welcome to Engineer's Home. Today I am going to show you the analysis of this frame structure and solve the problem as stated. We need to find the support reactions, we need to draw the AFD, SFD and BMD and mention the salient features as well. So as we can see in the frame, the supports are at different level and there is a moment over here with UVO, point load. So we will learn how to apply the inclined loads as well here. As we can see, 4 meter, 2 meter along the x-axis, and along the z-axis it will be 1 meter, 3 meter and 3 meter. So let's begin. I'll start with the new model. Then I can select blank for now and keep the units as kilonewton meter. So let's work in one window. So I would edit the grid data, modify source system. So 4 meter here, 2 meter here, 1 meter, 2 meter and 3 meter over here. So I would add, the first grid is at 4 meter and the other is at 2 meter, so it's total 6. For Z it's 1 meter and then the other is at 3 meter and total height is 6 meter. So okay, as we can see, so let's assign the default members for now. We don't need to design the frame, so for analysis we follow the line diagram only. So as you can see, the grids have been formed. Let's draw the default frame object. We just need to analyze the structure, so we don't need to define the properties of the frame object. So I draw one frame element from here to here, then over to here, then here. I click, and the other one is from here to here. So the frame elements are drawn. Now let's assign the support. It's hinge support at both ends, so I can select both ends. Assign joint restraints. So hinge support restrains the vertical and horizontal movement. So apply. So hinge support has been applied. Now let's assign the loads. Let's see the load patterns first. We are not going to take the self weight of the beam of the frame elements into consideration, so we put 0 over here. Okay, so we apply a UVL here. The value of UVL is 10 kilonewton per meter at the end. So assign frame loads distributed. The direction is gravity direction. Okay, so I can choose the absolute distance, and at 4 meter I can assign 10 kilonewton per meter. Apply, close. So as you can see, the UVL has been assigned. Let's assign a point load over here, here and here. So here is 20 kilonewton and there is 30 kilonewton here. Assign joint loads, forces. It's in the downward direction, so force is negative along the negative z directions, minus 20. Apply, and at this point, sorry, there is no point, so I need to assign a point over here. I can select the frame, define, draw special joint. Okay, so as you can see, the joint has been drawn, but from the figure we can see that the load is applied in inclined manner at an angle of 30 degrees. So there are two ways of doing it. Either we resolve this in x direction and y direction and apply two loads in two directions, or we can define a new grid and rotate that grid and apply the load in that grid. I can show you in SAP. So let's edit the grid data. Let's add new system. In the new system, so it's for point load, I can say new grid. So as you can see, ZX is the direction, so for now I need to rotate the x-axis by 30 degrees so that the load is applied in that direction. So I can rotate about global Y, so 30 degrees. Okay, so now I can select the joint and I can assign joint loads. So here I can choose the new grid pattern and I can apply 30 kN force at X direction. Let's see. So as you can see, the load has been applied over here. So this method can be very useful. The total loads have been shown and the software automatically resolves the loads provided in an inclined manner. And one thing more here, there is a hinge support, internal hinge over here, and rotation about this direction is given 40 kilonewton meter. So I am going to apply a moment of 40 kilonewton meter over here. So it's in the global grid and it's the moment. So the moment is rotating the XZ plane, so direction is going to be in the Y direction. By right hand thumb rule, the direction is going to be inwards from the screen, so it will be positive. So the value is positive 40 kilonewton meter. So as you can see, the moment also has been applied. Now let's assign the internal hinge over here. Let's select the member, this member, and assign frame. We are going to release the restraint, so we are going to release the moment. So this is the starting point for this frame, so it's going to be at the start. Apply, and for this frame it's going to be the end point, so it's going to be end, apply. So as you can see, the internal hinge presentation in the model looks like this. So our modeling is complete. I can select the exit view now. I can select the display. Oh, this was our loaded structure. So now let's analyze the structure. Let's set the analysis option to 2D exit plane. Okay, run analysis. I run off this case, turn off the model case, so I begin run now. Let's save the structure as frame 2. Save. So the analysis has been completed, and let's see the required diagrams. So our first question was to find the support reactions. So let's display force stresses joints, apply. So the support reactions are as shown for the hinge, there are two support directions along horizontal and vertical direction, so you can check that. So now let's see the respective diagrams display. So first is stress diagrams and that. So let's check the axial force first. You can see the values from here, or we can select the structure. Let's see the shear force diagram. Okay, we can see the shear force diagram as well. So there is no any point of zero shear force. We can see the values from here. Moment M33 apply. So our bending moment diagram looks like this, and at internal hinge it's 0, so we can also select the member from here and see the values, or we can display the show values options. So this much is for this problem. About mentioning the salient features, we don't have any point of contraflexor or the point where shear force is 0. So that's it. Thank you for watching.